Hello everyone, I am Jimmy. Today I'll be presenting on joint work done with my master student Pons and my advisor Armando Solizama. This is Bob. Bob is writing a social network and possibly doing a graph search on it. So he has to write his social network with a lot of code in multiple layers to display a profile page, shows the photos, has to fetch them from the database. One day, the media attacks Bob. There are privacy bugs in his social network. Uh-oh. To fix them, he needs to re-architect his code. When getting the photos from the database, it needs to know who is going to see them. That means it needs to add up this parameter, the viewer parameter, to every layer of the code. Facebook had to do this in 2010, adding a parameter to thousands and thousands of functions. It took thousands of man-hours. A few years later, Dropbox had a different problem with a similar solution. This was their largest project for the year of 2014. Thousands of man-hours adding parameters to functions. This is Patty. Patty is a program transformation expert. And she thought, maybe I can write a tool. There's an opportunity here. I can write a tool for this problem, sell it to both Facebook and Dropbox, and make a lot of money. But there's no opportunity here, because they're in different languages. And the way we build source-to-source transformation today, there is no way to reuse the code for different languages. We've only found one prior attempt at this problem, and they were not able to scale to multiple real languages. But today, we will do so. We have a new representation called incremental parametric syntax that makes it possible to write a single source-to-source transformation and run it on many real languages and get human readable outputs. We've implemented this in our Cubix framework for C, Java, JavaScript, Lua, and Python. And we have indeed prototyped Patty's tool for 5 languages simultaneously. Suppose you want to write a source-to-source transformation for 2 languages that have some parts in common, and you want both versions to share work. Okay, maybe you can do this with an intermediate representation, but actually this does not work. How do you build such an IR? Well, you could do it as a least common denominator, which means you boil down both languages to simpler components. But this loses a lot of information, and so what happens is that it tends to mutilate your code. In particular, a common effect is that it will turn all for loops into while loops because the IR lacks for loops. An alternative IR design is to use a union of languages approach. But now this loses information about what's not in the language, and so it's easy to confuse the different features. And we've actually found examples of Clang where there were Objective-C features in what was supposed to be pure C code. And in fact, if you do any kind of IR approach where you write a program transformation as a transformation from a type to itself, then you've already lost. You cannot write modular code across languages this way. And in fact, this follows from the theory of subtyping. So the language agnostic approach is out. Let's go language-parametric. What it looks like is that you will write a program transformation for any language that has certain syntactic features like variable declaration in blocks, and also a few language-specific operations. And another view of this, which we do, is that we go from languages to language fragments, where instead you break your language into many pieces of different attributes, write your transformation in each one, and you put them together into many ways. And that's how our system works. The representation that makes this all possible is called incremental parametric syntax. Here's a normal example of a syntax definition. The syntax is given as a set of mutually recursive data types. But the mutual recursion is a huge problem for modularity, because it means that if I want to just look at that single while node, it in turn depends on all the expressions and all the statements of the language. And so because of the recursion, there is no way to write code that only cares about a single node type without being constrained to every other piece of the language. Over the last 10 years, we found many ways around this problem, different ways of doing modular syntax. And all of them work on language fragments instead. What does this look like? So there have been multiple approaches, but the one that we use is called data types a la carte. And basically the big idea is, instead of saying I have this add node, its children are expressions, now you need to know what an expression is, all the kinds of expressions that could ever exist. You say, this is an add node, we're just going to look at the node. What are its children? I'll tell you later what an expression means. And this lets us isolate the node from the rest of the language. And now we can build up a bunch of these different language fragments and put them together. So this prior work gets us to a giant pile of Legos for different language fragments. Somehow, from these Legos, we need to build Java. So I don't really want to do that. Instead, what I'd rather do is start with an existing language definition that someone else has built, and just reach in and make small changes, so replace a few parts. And that's what we do. We can take a language and decompose it into generic and specific parts. We then write a programming transformation that works only on the generic parts, plus some language-specific operations, and then recompose it back together. So how do we do this? Well, say we wanted to take a bunch of languages and replace all their variable declarations with a generic variable declaration node, so we can write transformations against this generic variable declaration. It has an optional initializer, a name, and the variable declaration attributes. What are these variable declaration attributes? In Java, it's a type. In C, it's const volatile register int star. It's a bit more complicated. So we need a way to modularly say what these variable declaration attributes are and have it be different per language. And we do this with a small idea that solves all the problems: sort injections. We declare that Java type is a subsort of variable declaration attributes in Java, whereas in C, a variable declaration attributes is a list of type qualifiers and sort specifiers, and actually it's more complicated than this, but C. So we want a way to modularly specify these subsort relations, to modularly specify what edges may be in AST. How do we do this? Well, we already know how to modularly control what nodes may be in AST. That's data types a la carte. So we just turn edges into nodes. To say that Java type is a subsort of variable declaration attributes in Java, we give Java a new node called Java type is attributes. And from this, we get our actual representation of programs. We get these sort of mixed trees, where it goes, here's Java-specific code, sort injection, and that's the glue that jumps us over into generic node land, where transformations live, and there's sort injections back into Java-specific land. How do we decide what things should be generic and what are left as Java-specific? Well, you only do as little as you can get away with. Your transformations need the generic nodes, but you only need some of them. So you only make some of the nodes generic at first. Later on, you can make more Java nodes generic. And so that is the incremental in incremental parametric syntax. Because we don't need to do all this work of building our language out of Legos from the get-go, we are therefore able to add new languages to our system in under 2 days. Our transformations do not only need to look at the nodes, they also need to know the relations between them. So in both C and JavaScript, assignments can be used as elements of blocks. But there are a lot of details in between that are different. But sort injections save the day once again, because all we need to know is that an assignment can be used as a block item, and that is also a sort injection. And so from this perspective, you can kind of think of transformations as working on these blown down trees, where in reality you have a really complicated tree with all the language details, but you extract it down to just the generic nodes and the relations between them. And that's what our transformations work on. So we've implemented this approach in our Cubix framework and added support for C, Java, JavaScript, Lua, and Python. Here's the Cubix architecture. I'll point out just 2 things. One is that we don't need to write our own language definitions and parse in preprinters. We actually generate bindings to existing ones that I can just download from the internet. And the entire point of this is that we bring a language into this incremental parametric syntax. And once we have that, that really does all the work for us of making language parametric transformations possible. It uses a data types a la carte style representation that makes it very easy to switch between generic and language-specific code. To have statements in C, you would say term of the C signature of sort statements. But you can generalize these as you will to get different levels of detail about a language. For instance, term f assign L refers to assignments in any language, whereas term javasig s means Java terms of any sort. Term f ident L, where assign is a subsignature of f, means identifiers in any language that has assignments, and term f ident L in a language F satisfying there's a sort injection from ident L to the positional argal cell, and there's a call analysis for F. These are identifiers in any language where identifiers may be passed as arguments to functions, and where there's someone else has written a call analysis for F, which may be either written generically or language specifically. So this representation makes it relatively straightforward to begin writing our transformations. Here's an example of the simplest transformation we can think of. This is elementary hoist. It will lift all variable declarations to the top of the block. And here's the code. The core of the code, the generic part, fits in a single slide. The language-specific part is a lot simpler than this. And despite its length, this code here supports C, Java, and JavaScript and passes 98% of compiler tests. The more complicated version also supports Lua and passes 100% of tests. So what can we do with this? Earlier gave the story with Facebook and Dropbox. So we've implemented this transformation of transitively adding parameters to functions. It's called the Interprocedural Pluming transformation. It took us 40 hours to implement it for 5 languages simultaneously. That is one new tool for your favorite language every single day on average. And although this is a prototype, it was still good enough that we were able to do a 500-line refactoring across 41 files in a 20,000-line code base. That was our realistic transformation. We've also done several semantics-preserving transformations, which are easier to test. But these are still pretty complicated. This is the 3-address code transformation. It removes all nested sub-expressions. So if you have f and g of 1 plus 1, you need to hoist that out to a temporary variable. You need to compute that before the loop, but you also need to handle short-circuiting. And you also need to compute this before the end of the loop. And you need to declare the variables, but only the first time. So this is a pretty complicated transformation, even for one language. With a single code base, we implemented this for 3 languages. Well, we collected over 500,000 lines of compiler test suites, covering every language corner case in the book. Some of these tests we could not use. The test assert this function is declared on line 37, which is surprisingly common. That test would fail under any reformatting, so it should not pass. But for the rest of them, we got all 3 transformations to 100% pass rate, with one exception, which is that we found and confirmed a crash bug in Java C. Finally, we need to show that unlike the IR approaches, we do not mutilate your program. We produce human-readable code. So bring in the humans. We ran a Turing test. We recruited humans, do the same transformation as my program, and we sent both versions to Mechanical Turk. The Mechanical Turkers rated both. We built a new benchmark sets, real-world unchained semantics, 50 functions from top GitHub projects, and a test suite thorough enough to detect any semantics breaking change. We sent these functions both to my computer and we recruited humans. Both versions were sent to Mechanical Turkers, who rated them 1 to 5. Our goal was to show the computer ones were at most 1 star worse on a 5-star rating than the human ones. We proved that with p less than 10 to the negative 8. This hypothesis was clearly far too weak because actually we found that overall the computer rate transformed ones average slightly higher than the human ones. We're not sure why. So we've come very far in building multi-language transformations. We've shown that it is possible to share most of the work between similar transformations of different languages. And yet, this is still flexible enough to be tuned to the language and handle all the language corner cases. We can even get to realistic transformations. This has been a very long and intense project. I'd like to thank my many collaborators. We are actively seeking collaborations. If you want to write a multi-language tool, come talk to me. It's great to have you all here today.
Questions?
Hi, thanks. So you motivated this work by arguing that a program transformation expert should be able to use this toolkit to write program transformations. Can you talk a little bit about your experience having people other than yourself, other designers of the system, actually using it and writing program transformations?
Yes. So this requires some pretty advanced generic programming stuff. So our tutorial elements have gotten better over time. We do have someone here who is not me, and was able to write some transformations. So it is possible, but this is very much an expert system at the moment.
Hi, Ben Zorn from Microsoft Research. Yeah, a great talk. So in terms of the Mechanical Turk experiment, how did you account for variability in the quality of the human responses?
Okay, so the two parts of the human responses, the people who were actually doing the programming transformations, they were not from Mechanical Turk. We recruited them from MIT and from the internet. The Mechanical Turkers, they're rating them 1 to 5. So we employed a few measures of quality control. One is that we did several dry runs, and we found that 11 seconds is the magic number, where they were making people who were clicking faster than once every 11 seconds were making questionable decisions. If they clicked too fast, we locked them out of all experiments forever and threw away all their data. Second, we had several canary questions, where there were things like, here's the original program, here's the transformed version, here's a completely different program. They better rate the completely different program lower than the correct version. Or here is the exact same copy of a program. You better rate them both the same because we're showing you them side by side.
Just a small question. So is your framework only for transformations, or can it be also used for analysis, metrics, analytics, mining, this kind of stuff?
It can also be used for analysis. Its real strength is in transformation, because for analysis you can also boil things down and use an IR, and people have done that for a while and it works pretty well. But as long as you have these generic nodes, you can and write. So actually, we use a very bad call analysis for the interprocedural plumbing transformation that just looks at names. And we did, in fact, write then 20 lines of code for 5 languages simultaneously. So having generic nodes shared across languages helps for everything.
Can you have any queries while you're writing transformation? Because, for example, when you add this extra parameter, it could be the case that you already have a local variable inside and you change the semantics while adding this parameter.
I missed a keyword. Can we what when writing a transformation?
Some query or predicate that I don't want to. So when I add an extra parameter, I want to make sure that there is no local variable.
So this is a framework, so you can do whatever you want. And in fact, in the interprocedural plumbing transformation, it will prompt you before it makes every change.
Okay.
Any other questions? So I have a question. So it seems you can apply transformation to multiple languages because the languages are semantically very close, right? Because you're basically doing syntactic transformations. Is that true, or?
Some of the transformations we presented actually operate on the control flow level. So I gave the example of the 3-address code transformation, where it will have to hoist a loop condition before the loop, at the end of the loop, and before every continue statements. And that's done by acting on the control flow graph. And we were also able.
So you have a generic approach to doing control flow analysis?
Yeah, so we were actually able, our representation made it possible also to share a lot of work when writing control flow graph generators for all 5 languages. So because of that, we were actually able to average 100 lines of code for a really good control flow graph generator for each language.
And the same for name and type analysis? Is that
Our name and type analysis is pretty primitive at the moment, but our control flow graphs are pretty good.
Okay. Any other questions?
Kind of along those same lines as that question. So do you think there are languages for which this kind of a framework would not be able to function as well as it has for the languages you've studied?
I have no idea how to make Prolog share anything in common with the others.
You talked about readability as a metric of measuring success. Were there specific things you did to sort of keep the readability high? I didn't quite see the correlation between your framework and what you do to maintain readability of the final output. Like, I know you can avoid name mangling and such things, but do you do other things too?
The main way that you mutilate code when using IR is that you lose information, in particular doing things like changing for loops into while loops. And because we don't use an IR, we have a separate representation for each language which shares parts. None of that happens. And so we are actually able to do a full round trip where you can go from an original parse tree given to us by the third-party parser through our fancy language incremental parametric syntax and back, and it will preserve everything.
Last question.
In your examples, in the first example you showed where you want to add an additional parameter to a function, and I presume find the call sites and update the call sites. What would happen if you can't find the call sites? If the call sites are indirect or partial evaluation? Or
Then, yes. So that transformation is in fact, its quality is based on how good the call analysis you feed into it is. So if you improve the call analysis, then the quality of refactoring goes up. But the thing is, however you do it, it is going to require some human interaction anyway, because at some point you need to decide where and how to provide that parameter to begin with.
All right.